Please introduce yourself and briefly summarize your education and professional background.
Hi, I'm Steve Bourne. I am a master's degree in civil engineering, which I got at Georgia Tech. There I focused on civil engineering, software engineering, and climate science, which kind of makes me a little unusual, but definitely leads to building a tool like Simulator, which we're going to talk about today. In terms of a professional background, this is my 20th year at AtkinsRéalis, which I joined right out of grad school. And during that time, I have built a lot of decision support tools and software like that, focused on a variety of subjects, all really kind of focused on planning and engineering.
All right, so now let's talk a little about this simulator that you alluded to. So what is it and what is your role with AtkinsRéalis as its project director?
Yeah, at Atkins, I'm a project director in general, which means that I oversee portfolios of engineering projects, which are focused on construction and design. With Simulator, that's actually something we came up with in 2010, 2011. Way back then, we were challenged at that point to come up with an offering we could give our clients. And we sort of pinpointed mid-sized cities as the ones we'd like to help to understand their resiliency and figure out what they could do about it. So we developed an offering which is really sort of focused on their master planning process and being able to stress test the master plans they were coming up with against what we knew about future climate and how that was going to change. So City Simulator was born out of that, and the idea with it is you create a digital twin of your city and you evolve it into the future, 80 years into the future, with projected climate change, and understand where the weak points are, even if you enact your master plan. And how can they be addressed? How can you incorporate resilience-focused solutions, things like elevating houses so they won't flood anymore, those kind of solutions, into your master plan, and therefore increase the resilience of your city. So I was instrumental in coming up with that idea and building City Simulator from the start. And I've been using it ever since in my role as a project director to do resilience studies and those kind of projects.
So when you were starting, when we come up with this idea, why did you pinpoint mid-sized cities as well as resilience? What was I don't know, is it like a market opening, or did that just kind of fit with what you were working on at the time?
Yeah, our global CEO for Atkins, now it's called AtkinsRéalis, but then it was called Atkins. He came up with a challenge for all of the regions in our company. It's a global company called future-proofing cities. He said, okay, resilience is a word that's starting to be popular now. Our clients are worried about that, and across the board, not just cities, but runners, transportation departments, and nuclear power plants, and almost everyone was starting to get worried about that. And this was, I was in the North American region in the company, and this was sort of our response to his challenge, the Future Proofing Cities challenge.
Okay, and why mid-sized cities as opposed to small cities or larger cities? Or was that just a place to start, or this just where you went from?
Yeah, we kind of figured that we needed to start somewhere. And clients at our company and their portfolios, they're very different, like what they actually need to do. So we needed to sort of, you never build anything if you go too general from the start. So we needed to sort of pick something and go from there. And we had a lot of mid-sized cities clients. They had a lot of very clear needs and objectives. And so we thought the idea would just work very well in the medium-sized city realm. Since then, we found that, like I said, every client needs a resilience assessment. So the smallest one we've done was one building in Florida for the Florida DOT, which was, essentially built very close to a floodplain. And we did an assessment of, what the building actually does is it facilitates assessments of vehicles. So it's a fleet assessment facility. We essentially modeled that process, trucks coming in, getting lifted, getting maintained, and so on, and then driving back out. And we modeled how much is that going to be interrupted over the next 80 years by flooding, basically from the river, from tides, from all the different sources that climate change is going to bring flooding. So that's the smallest one we've done. The biggest one we've done is the global supply chain, moving from Asia through the port of Prince Rupert and down to receiving hubs like Chicago, and all of the different climate change influenced events that'll impact that supply chain over the next 80 years. In that case, it was we were simulating every container of cargo essentially moving from Asia through that port and then down to receiving facilities for the next 80 years. So millions and millions of cargo containers. Yeah, that was a really interesting one. But that's the range, and we've done everything in between: small cities, medium cities, large cities, 200-mile transportation corridors, full states. Right now we're doing the Alaska Highway. It's an 800-kilometer corridor in northern British Columbia. So the concept of a simulator has lots of applications, and we've definitely seen that borne out over the last 14 years.
All right, before we get to kind of a description of how this exactly works, I believe that there's a new product called the simulator that builds off of City Simulator. Is that correct? And if so, how are they different?
Yeah, that's right. Simulator is sort of the upscaled version of City Simulator. Like, we had recognized almost from the start that we weren't just going to be modeling cities. So to say, okay, we see that you have, your military installation, and we're going to use City Simulator to evaluate it, it just didn't really make sense. So we came up with a set of sister products called, Seaport Simulator, Airport Simulator. But in our upscaling process, we've been taking the tool from basically just being a US-based tool to a global tool. We decided to, change the name and really sort of name it more what it is, which is a simulator, and put the tagline for what the application is at the end.
All right, that makes a lot of sense to me. Now, this is going to be complicated, so feel free to take your time. But I'm hoping that you can kind of guide me through how a resilience simulation works. Is there like a digital twin creation? Where does all of your data come from? And why do you choose these sources? Again, that's very complicated. So maybe choose an example that you're very familiar with, and kind of run me through what that looks like when that simulation is done.
Yeah. So there's a workflow to it. You kind of go step by step. We at AtkinsRéalis, we have teams of experts, of climate scientists, planners, engineers. They all follow this workflow using the tool. So the tool is really, a tool that we use within Atkins to do the work of resilience modeling. The workflow, it starts with essentially you say where in the world you want to do an analysis, and we have whole global databases of populated places like town boundaries and so on. So you start with a map of the world. Basically, you pick the point where you want to do your analysis. That starts bringing data in from databases we already have set up, the data about things like population, number of jobs, the transportation networks, and so on. So that's kind of gets you started. The next step is research. Very important in these studies to understand who's proposed resilience solutions previously, and what were they, and what was found out about them. So we have a whole tab within the tool where you can bring in the literature review and start to pick out projects that have been evaluated before. This actually plays a role in the final analysis when we do it. You have an assessment setup process that you do. There you can select things like if you want to do an analysis that's focused on a framework that's already been set up for resilience, something like the PIVC framework in Canada, which is a certain set of objectives and an objective way to measure your resilience. You can pick that, and from there on, the tool is sort of aligned to the requirements of that framework. And when it does its calculations, it does them according to the objectives and metrics that that framework prescribes. You could also pick what grant program you're going after in case you're compiling this report to go get a grant. And in that case, it'll put the results in the form that the grant's looking for. So it's very valuable to do that. After that, we get into forcings, driver forecasts is what we call them. This is the rainfall, the temperature, the sea level, the wind, these variables they're going to drive our simulation. That's why we call them driver forecasts. They are compiled by mixing historical data in the area that you're focused on. Say like we did City of Clearwater, Florida recently. So it'll pull the historical data for that area from databases that we're tapped into that are hosted by places like NOAA, NASA, USGS, and so on. It also pulls in global climate model projections of these variables, future rain, future temperature, and so on. The tool provides you capability to blend those two things together and make a daily forecast of each of those variables, which will become the forcing, the drivers of the simulation. So that's one thing you need. The next set in the workflow is the digital twin part, where we're doing very exciting stuff at this point. Traditionally, what we did was, the digital twin for us for a city is usually the buildings, the parcels, the roads, the utility systems, the people. City simulator, I'm still getting used to saying it, is actually an agent-based model. So there's 1 million people in your city. We have 1 million avatars rolling around in our simulation and doing things. And this is how we get to know, where the disruption actually is and what the operations of the city, how they will actually be disrupted by future events. So we have to pull all that information together. Traditionally, it's been a painstaking process. Like that is a good portion of the work we have to do one of these studies is just to get all that information. For houses, you would have to go to the tax assessor database, download that database, scrub the data looking for what you need, like the specific attributes of each house, get that into another database, and do the same thing for all those different data sets I just mentioned. It would take months to do that. Lately, we have been tapping into APIs that have this information so that it goes from 3 months to 3 seconds to pull your digital twin together. People will immediately ask, okay, how, if you're doing that, are you sacrificing the quality? And so that's really the problem that we're solving right now, is to identify the gaps after we pull in that information from APIs and make sure that we're filling the gaps and making sure the data is high quality. But I'll give you an example. We did Fort Lauderdale International Airport a couple of days ago. And we said, okay, here's the airport. We just zoomed to it on a map and said, give us all the buildings, the apron, the concourses, the gates, the runways, the taxiway, everything about that airport. And the tool tapped into OpenStreetMap's global database of GIS information and pulled it all together in 3 seconds and presented us on the map. Here it is. Hadn't actually done that before. So, like that data didn't exist on our machine at the time. Press the button, 3 seconds later, it did. That was pretty impressive. But anyway, okay, so we get the digital twin together. Then we go into simulation, and what we've tried to do to make the tool very accessible to our global network of professionals is to do a no-code configuration solution. So instead of writing the code that tells it how to simulate, we have this sort of nested loop diagram, which is how the tool actually works. It does, a year each year on the outer loop and each day on the inner loop. And in the outer loop, it simulates like sort of growth of the city, adding new buildings, adding new people, adding new infrastructure, and so on, and assessing things like carbon footprint. And in the inner loop, it runs once a day, and there it's paying attention to the global climate signals. So it's taking those driver forecasts and saying, did a disaster happen today? If it did, it evaluates across the city, where were the impacts? And works in a daily loop like that for 80 years. So the in the no code configuration step, you can actually say what you want to simulate. You can turn off climate change simulation if you want. You can turn off like if we have electric vehicle simulation, you can turn that on and off. And all the different steps. There's more than 100 different check boxes basically, and you can just pick the set that actually answers the questions you want for your study, and then you hit simulation in the next part of the workflow, and it actually does the simulation. The simulation actually works in a scenario-based way. So the first simulation we ever do is the base run, and in that simulation we don't add any adaptation or mitigation options. There's no optioneering, right? So you're just evaluating what are the vulnerabilities of the city with the current plans that it has. So you can run that, and then you can start to run other simulations where you add in new adaptation and mitigation options. It works like a toolbox. So we essentially say, try out elevating homes, acquiring homes, planting trees, economic development zones. We can actually pick which ones we want. And then the tool, when it runs the simulation of the scenario, tries every combination essentially of those efforts. So every house in the city, we try to elevate it if needed. Every house we try to acquire it if that makes more sense economically, and so on. And it finds the best set of solutions for the budget that you have. So you say, I have $50 million a year, figure it out. It finds the best set of solutions to increase your resilience as much as possible. We're pretty far in the workflow at this point. At this point, you start recording findings about what you're seeing. You can do that in the tool, and it just keeps a record with images, maps, tables, whatever it is you're calculating. And then finally, you can make a set of recommendations based on those findings, where we bring in a database of possible adaptation solutions, and you say which ones are recommended for this particular study. And the final tab in the workflow is reports. And we're doing really cool stuff there, where we're using like AI-based approaches to draft reports and pull in your findings and record exactly what data you use. That becomes very important. And really sort of pull together a full 100-page PDF report from the assessment that you've done. So that was a lot of workflow, but but that's actually what we do when we do these studies.
Wow, that's impressive. That's a very detailed and complicated. It sounds, like I'm used to hearing that a lot of different things involved in there. It sounds like you're using like GIS stuff, you're using like maybe gaming engines to get that kind of avatars and simulations. Are you guys using all these in-house products, or are you using external products to kind of build your own simulator?
We have pretty much built it from the ground up. It's all our code. There are, in coding these days, no one builds everything from the ground up. You use plugins and open source, modules. But for the most part, all of the thinking in there, all the algorithms, we try to integrate where we can to speed up the process, but very often find that we do have to write our own code for some things, and we integrate those. But we're very careful to, instead of saying this is the method in City Simulator, we'll put a drop down and say you can pick which method you want, right? And so we're open to changing the methods we use and expanding those toolboxes as much as possible.
So am I right in understanding that Simulator is kind of an internal product, like only used by AtkinsRéalis engineers, and it's not something that, let's say, a client would be interfacing with? Is it like you're kind of selling the simulator service, but using it all internally? And like I said, it's not something that someone from the outside could access and use. Is that correct?
To date, that's correct, but we're getting a lot of pressure from clients to use the tool, um, particularly around and even though we're making this digital twin building an easier process, many of our clients don't really want to do that part. That's the tedious part, and it takes quality controlling the data to make your model a quality one that produces quality results. So what our clients are really kind of interested in is just seeing the results for one thing on a map. They're very visualized within the simulator, and being able to rerun their scenarios, create new scenarios and run those, and really be able to kind of kick the tires on our assessments. So I predict that our clients are going to be using the tool pretty soon. I have several different opportunities to make that happen. Maybe the most exciting one is we're working right now with a group of students from Columbia University, which is one of the premier climate science focused universities in the world. They want to use City Simulator to do a New York City study on heat and flooding in urban and high traffic environments. And they want to use Simulator to do that. So we're myself and another colleague at AtkinsRéalis, we're advising them on their capstone project and hope to allow them to use Simulator to do the project.
How do you feel about how the climate data is evolving to fine tune your models? Do you think that it's going to keep getting better and better, and that these models are going to continue to improve to create better simulations, I guess?
Yeah, absolutely. As computing power grows and as interest in the subject grows, which it's 100 times more interest in climate science right now than it was when I was doing it at Georgia Tech in the 90s. Just enormous interest in the subject. So as all that's grown, the the resolution of the data sets, they've gone from 200 kilometers down to 50 meters, that kind of thing. The skill sets that are used, I mean, the algorithms and their precision and complexity has grown substantially. It's a very open science kind of world. So if you have an idea for an algorithm, you can implement it, and that there's been a lot of that as well. So the choices of interpretations of the future has really ballooned. And for the climate scientist doing a resiliency study, that's really helpful. We kind of go with if there are 50 opinions out there about what the climate's going to do, and 47 of them agree with each other, that's probably what the case is. And so having the 50 opinions about what will happen in the future. In the 90s, there was one opinion. So going up to 50, it really actually helps with just making the studies more helpful and more valuable.
It sounds like you're pulling in an incredible amount of data from a wide variety of sources. How are you, quality controlling the data that actually gets into the simulator and making sure that it's good and useful?
Calibration and accuracy in any model is something you just have to do to make sure the model is providing a valuable result. And what we're doing is we're integrating dozens of models together. So what we do is we make sure that first they've been calibrated in the first place, like whichever investigator did that modeling, that their calibration was of high quality. That's where we start. Integrating the models together, like if we have a global climate model projecting rainfall, and we have a flood model taking that rainfall and showing what happens from a flooding perspective. When a flood occurs, that introduces its own set of uncertainties. So what we do is we try to compare it to reported flooding or reported impacts of disasters in general. So we can take our simulation, put it together. It'll say this is where it thinks the flooding is going to happen, and we'll use this flooding as a hazard example. We'll then, our clients like the North Carolina Department of Transportation, for example, after a hurricane, they send out drones to record where did the flooding really happen, right? And so what we do is we compare our projected flooding to the drone footage. And you'd be surprised, like we'll do an entire corridor 200 miles long, zoom into a specific place where it floods, and the polygon of the floodplain that our model made matches almost exactly to the flooding in the drone footage. That's one type of calibration. Other parts of our model, they're predicting things like the number of trips on a road, the amount of freight revenue being generated. There's lots of different metrics. We try to compare to all of those and make sure we're as close as possible to what's been recorded. In the end, though, it is the future, and the quote is, prediction is very difficult, especially about the future. I think that was Niels Bohr. Very true here. We take a very pragmatic view of that and say, let's look at the worst case and make sure that whatever we're recommending here will handle the worst case. So we're less focused on what exactly will happen in the future, and more on what do we need to protect for. So that's a very pragmatic way of looking at it, and really kind of serves to help both us and the clients in putting these assessments together.
Okay, so I'm wondering, after the simulation is done and you've created this amazingly detailed report and recommendations, what happens next? Are free to take your report and have someone else make the designs or construction, or is it kind of because Atkins supplied the simulation, are you expected to be the one who takes that next step for them?
Oh, it's a mixed bag. In many cases, no. I mean, public entities will disengage one activity from the next, and it's whoever provides the best proposal is the one who gets the work. And in some cases it's actually, I don't remember a case where we were hired to both do the resiliency study and then do the follow-on construction work. That doesn't regularly happen, no. But I like to think that from doing these analyses, we build an incredible understanding of the transportation corridor or the city or whatever we're studying, and that gives us an edge in winning the next projects down the line. Just being able to build something like simulator, I can just give you sort of a personal viewpoint. It's really exciting to do something like that. You hear of, and I actually, I have 20-something kids, and they had climate anxiety growing up, and you hear that's not an uncommon thing. The thing that was missing, that from my kids and certainly from society in general was, is there something we can do about it, right? So being able to provide something you can use to do something about it, that's been extraordinarily rewarding in my career, and I just wanted to give you that sort of personal viewpoint on it.